Namaskar. In today's video, we shall discuss about the general forms of an ODE of first order and first degree. Then we shall move on to the definition of total differential, and finally we shall try to understand what do you mean by an exact ordinary differential equation. So let us start this video. Now see, these are all examples of ODE of first order and first degree. Now all of these equations can be written in a common generalized form. Let us see how. See, for the first equation, you can write this as dy dx equal to x square minus y square. You could put y square that side, x square minus y square. You can write this one as the second one, which is dy dx plus x square y equal to sin x. You can write this as dy dx equal to sin x minus x square y. And similarly, the third one you can write dy dx equal to x square minus y divided by y square plus x. See, all the three ODE which were of first order and first degree was converted, can be written in this form, that is dy dx equal to some expressions of x and y. So in general form you can write that any ODE of first order and first degree can be written as dy dx equal to some function of x and y. This is called the general form of an ODE of first order and first degree. Now this general form is called the derivative form. Why? Because you have derivative dy dx over here, dy dx equal to function of x and y. Now there is another form which you can write for first order and first degree ODE, that is called differential form. What is that form? Let us see. Now again see, for the first example you can write this one as dy dx equal to x square minus y square, which implies you can write this one as x square minus y square dx minus dy equal to 0. So if you cross multiply over here and put dy that side, so x square minus y square dx minus dy equal to 0. Now for the second one also you can write this one as, see, dy dx equal to sin x minus x square y, which was the derivative form. Similarly, you can convert this into this form, sin x minus x square y dx minus dy equal to 0. And the last one, what you had, y square plus x into dy dx plus y equal to x square. So you can write this one as y square plus x dy dx equal to x square minus y, or y minus x square dx plus y square plus x dy equal to 0. You can pause this video, take a look into these examples, try to calculate by yourself, and you will find each and every time you can convert whatever form the first order and first degree ODE is given, you can convert that form into these type of forms. Now if we have a close look into these type of forms, you have differentials involved into it, dx dy. And if you have to generalize this form, what is the form? See, for dx you have some function of xy, and for dy also in general you will have some function of xy as the coefficient. So in general you can write this form as some function of xy into the differential dx plus another function of xy into the differential dy equal to 0. Now the previous form was called derivative form, but in this form you have differentials involved into it. So this form will be termed as differential form of an ODE of first order and first degree. So in general, any ODE of first order and first degree can be written in any one of these two forms. In fact, these forms are interchangeable. If it is written in one of these forms, it can be converted into this form or vice versa. So what was the derivative form? dy dx equal to some function of x and y. Similarly, the differential form was some function of xy into dx plus another function of xy into dy equal to 0. In fact, throughout this chapter, we shall see the second type of form, that is the differential form, will be much widely used, because it is in this form that you can solve the main topic of this chapter, that is exact differential equation. If the equation is the ODE is given in this form, you have to convert it into the differential form, and then we shall proceed for the further solutions. Now, before moving on to exact differential equations, the topic of exact differential equations, we shall have to know what do you mean by total differential. Suppose there is a function of x and y, phi x. Now, the total differential is denoted as d phi, which is defined as del phi del x dx plus del phi del y dy. What is the meaning of this? It means that if there is a function of x and y given, the total differential d of that function is equal to the partial derivative of that function with respect to x into dx plus the partial derivative of that function with respect to y dy. Now, what is the meaning of partial derivative? That you already know. Partial derivative means you have to differentiate this function. Suppose it is del phi del x. Partial derivative of phi with respect to x means you have to differentiate phi with respect to x, keeping as if y to be constant. Similarly, del phi del y, the meaning of this is that you have to differentiate phi with respect to y, keeping as if x to be constant. Now let us see an example. Suppose phi xy is x sine y. So that is a function of xy. So what will be d phi? D phi is del phi del x. So it will be del x of phi, that is x sine y dx plus del phi del y, that is del y of x sine y dx, which is equal to, now partial derivative of this with respect to x, that means you have to think y to be constant as if y is constant. So it will be sine y only dx plus del y of this as if x to be constant. So it will be x cos y dx. So this is how you calculate or how you actually find out the total differential of a function. Now let us say another example. Suppose you have phi as x square y. So how to calculate d phi? First, del x of x square y dx plus del y of x square y dy. So partial derivative with respect to x, keeping as if y to be constant, that is 2xy dx plus del y of this, that is x square dy. Similarly, suppose you have phi to be only xy. So what will be d phi? Del x of this, that is y dx, plus again del y of this x dy. So I hope you understood exactly what do you mean by total differential of a function, and given any function of xy, I hope now you can find out the total differential of that function. So after knowing what total differentials are, now we are ready to move on to the topic exact ODE of first order and first degree. So now the question is, exact ODE of first order and first degree, what does it look like? Given any ODE of first order and first degree, how will you understand that that ODE is exact? Let us see. Now, any ODE of first order and first degree, suppose in differential form, it can be written as some function of x and y into dx plus another function of x and y into dy equal to 0. Now, if the LHS can be written as differential, total differential of a function, then you can tell this ODE is exact. Let us see an example. Actually, examples define the definitions much more better way. Suppose an ODE is given y dx plus x dy equal to 0. Now this is an ODE of first order and first degree, which is given in differential form. Now if you look at this, first of all, what is m over here? See, m dx, m is y, and what is n? X. Now see, this can be written as d of xy. See, total differential of xy. What is total differential of xy? See, y dx plus x dy. You can apply the definition of total differential. You can move backwards to the video, see the examples of total differential. From there you can calculate what is d of xy. You will get exactly this line, this left hand side, y dx plus x dy equal to 0. So this one can be written as d of some function. This was the definition of exact ODE, which is telling that if m dx plus n dy can be written as d of some function, then that ODE is said to be exact. Okay. Now let us see some more examples. Now this example, it is telling that y square cos x dx plus 2y sin x equal to 0. This is an ODE of first order and first degree in differential form. Now what is m over here? M is that function which is with dx. So m is y square cos x. And what is n over here? 2y sin x. Now say this can be written as d of y square sin x. Total differential of y square sin x. You apply the definition of total differential over here, what it will come? See that this is equal to partial derivative with respect to x, that is y square cos x dx, plus partial derivative with respect to y, that is 2y sin x dy, which is nothing but the left hand side of the given example. So here also we are seeing that the left hand side can be written as the total differential of some function of x and y. So the definition was, if you can write m dx plus n dy as d of some function, then that ODE is said to be exact. Over here we can write, hence this given ODE is exact. Now this is the last example of today's video. Unfortunately, this ODE is given in derivative form, not differential form. So the first step is that you have to convert this derivative form into a differential form. Then we have to move on to the testing procedure of exact ODE. Now, see how to convert this one to differential form. Put this one in the right hand side and then do cross multiplications, and after a few steps you will get dy equal to minus y by x log x dx, or you can put this log x over here, so, and this you can bring this side, so log x dy equal to minus y by x dx, and finally you will get y by x dx plus log x dy equal to 0. So this is the differential form. M dx plus n dy equal to 0. Here m is y by x and n is log x. Now the question is this an exact ODE? If it has to be exact, then the left hand side, this y by x dx plus log x dy, can be written in d of some function of x and y. Let us see if it can be written as d of some function of x and y or not. Now, after having a close inspection, we can see that it can be written as d of y log x. Do this total differential d of y log x. So first partial derivative with respect to x dx, then partial derivative with respect to y dy. So at first partial derivative with respect to x, it will be y will be treated as constant because with respect to x. So it will be y del x of log x. So y derivative of log x is 1 by x, so it will be y into 1 by x dx plus then partial derivative with respect to y. With respect to y, x will be treated as constant, so it will be only log x dy, which is nothing but this line. Hence, this can be written, I mean the original form, this can be written in this form, d of something. That's why this ODE is exact. So to sum up today's discussion, we can tell that for any given ODE in differential form, mdx plus ndy equal to 0, if we can write the left hand side, that is mdx plus ndy equal to total differential of some function of x and y. Anyhow, if we can write mdx plus ndy equal to d of some function, then we can tell the given ODE to be an exact one. In the coming videos, we shall see some more examples of ODE of first order and first degree, the exact ODEs of first order and first degree, and a specific criteria that will make you understand the given ODE is exact or not. So stay tuned for the next videos. As of today, if you have liked this video, then share with your friends and follow my page, subscribe to my channel. Till then, goodbye.